Curvilinear coordinate systems 12. The u-v-z coordinates of an elliptical system are related to a set of Cartesian coordinates by this set of equations. And we've already done the scale factors in part B. We obtained the differential path length, area and volume elements, gradient, divergence, and curl. Now we will do part E. Express the position and the displacement vectors in the elliptical system. So we're going to start with our differential displacement vector, dr vector. Dr vector, once you know the scale factors, is very easy to calculate. It's going to be equal to HU EU hat dV. Now we already know the scale factor is a square root of sine hyperbolic squared u minus sine squared v inside the square root. This is, and that's HU du EU hat, plus we have the same scale factor for v, a sine hyperbolic squared u minus sine squared v, that's inside the square root, dv ev hat, and the scale factor for z was 1, so it's just dz ez hat. So this is just writing our results using the scale factors we've calculated in part B. So this is from part B. Now, the position vector r is going to have a component in EU hat direction. So RU EU hat plus RV EV hat plus RZ EZ hat. So this is what we need to calculate. And plugging in the position vector written in terms of Cartesian unit vectors and using the transformation equations, remember that x is equal to a cosine hyperbolic u cosine v, y is a sine hyperbolic u sine v. So x is cosine, y is sine, and z is equal to z. So the position vector is actually a cosine hyperbolic u cosine v in ex hat direction plus a sine hyperbolic u sine v in ey hat direction, and it is z in ez hat direction. This is the position vector. Now, what is the unit vector EU hat? The unit vector EU hat is 1 over the scale factor HU del R del U. So we need to calculate del R del U. Now looking at the first term here, I have cosine hyperbolic. The derivative is going to be sine hyperbolic. So a sine hyperbolic U cosine v ex hat. The second term I have sine hyperbolic, derivative is cosine hyperbolic, plus a cosine hyperbolic u sine v ey hat, and there is no u in the z term. This is going to be divided by the scale factor a sine hyperbolic square u minus sine square v, which is inside the square root. And you can see that the a's will cancel here. And this is going to give me my EU hat direction. Now, what is R dot EU hat? R dot EU hat, which is RU. It's going to be this multiplied by this, so the product of the ex hat prefactors, so it's going to be a cosine hyperbolic u sine hyperbolic u cosine squared b plus, for the y hat direction, ey hat, we have the product of these two. So this will give me a sine hyperbolic u cosine hyperbolic u sine squared b divided by square root of sine hyperbolic squared u minus sine squared b. All right. And I can see that I have a cosine hyperbolic u sine hyperbolic u, a common term here. In this parenthesis, I have sine square plus cosine square, so that's equal to 1. Therefore, I obtain the position vector u component to be a cosine hyperbolic u sine hyperbolic u divided by square root of sine hyperbolic squared u minus sine squared b. This is the u component. Now for EV hat, the second unit vector, EV hat, I have 1 over the scale factor HV del R del V this time. And let's take a look at that derivative. So here is V, so I'm going to get a minus sine V from this term, and from this term I will get a cosine V, and nothing from the Z part. So minus a cosine hyperbolic u sine V ex hat plus a sine hyperbolic u cosine V ey hat divided by a inside the square root sine hyperbolic square u minus sine square v. Again, the same thing, the a's will cancel here, and r dot ev hat will give me the rv, v component of the position vector. So this is going to be the x part multiplied by this. So I'm going to get cosine hyperbolic squared, and from the y part I will get sine hyperbolic squared. So this will give me minus a cosine hyperbolic squared u sine v cosine v, and then plus a sine hyperbolic squared u sine v cosine v divided by square root of sine hyperbolic squared u minus sine squared v. And at this point, I'm going to recall that cosine hyperbolic squared minus sine hyperbolic squared is equal to 1. So we can recall this. And we're going to apply it here. So in the sine v cosine v parentheses, minus a sine v cosine v parentheses, or minus a sine v cosine v parentheses, I get cosine hyperbolic squared minus sine hyperbolic squared. So this gives me rv to be equal to minus a sine v cosine v divided by square root of sine hyperbolic squared u minus sine squared v. And rz is equal to z because the scale factor is equal to 1. So I'm ready to write the position vector. The position vector r is equal to ru. What was ru? This term, cosine, the product of cosine hyperbolic and sine hyperbolic with a. So we have a cosine hyperbolic u sine hyperbolic u divided by sine hyperbolic squared u minus sine square v inside the square root in EU hat direction. And we have minus a cosine v sine v divided by square root sine hyperbolic squared u minus sine squared v. This is in EV hat direction. And then we have z in EZ hat direction. So that gives us the position vector in this elliptical coordinate system. All right. So since we already calculated the scale factors in part B, so going back to part B, HC is equal to 1, HU and HV were equal, a square root sine hyperbolic squared u minus sine squared v. The displacement vector is HU du EU hat plus HV dV EV hat plus HC dZ EZ hat, because dr is equal to del r del u du. Plus del r del v dv plus del r del z dz. So that's a simple result. Now for the position vector written in the new coordinate system, I need the component of the position vector in the EU hat direction, in EV hat direction, and EZ hat direction. And that is equal to the position vector written in the Cartesian coordinate system with the transformation equations. And to find EU hat, EV hat, and EZ hat, I have to take the derivative of the position vector with respect to U, V, and Z, and then normalize it, basically divided by its magnitude, which is the scale factor. So this is going to give me 1 over HU del R del U. So I have taken the derivatives here. Cosine hyperbolic becomes sine hyperbolic becomes cosine hyperbolic, and divided by the scale factor. And this gave me the position, the unit vector EU hat. Now this is going to be, I have to take the dot product of the position vector with EU hat to find RU, the projection of the position vector in EU hat direction. So sine hyperbolic, cosine square, sine hyperbolic, cosine hyperbolic, sine square. Sine square plus cosine square is equal to 1 with the a sine hyperbolic, cosine hyperbolic parentheses. So this gives me RU. Similarly, for EV hat, I took the derivative with respect to v and divided by the scale factor. This time I have cosine v derivative minus sine v derivative plus cosine v, and doing the cancellations here. And then I find r dot EB hat by multiplying this. So sine hyperbolic, cosine hyperbolic. So this is going to give me cosine hyperbolic squared, cosine v sine v. And then I will get sine hyperbolic squared, because I have sine hyperbolic here, sine v, cosine v. Cosine hyperbolic minus sine hyperbolic is equal to 1. This is something we have used many times. So with that, I obtain RV. RZ simply is equal to Z. Now I'm ready to write the position vector RU EU hat plus RV EV hat plus RZ EZ hat.